matrix column space. This is a concept which goes very close in line with the span, but this is a concept which exists specifically in n-tuple space. So what you do is this: you just fix a matrix, not necessarily square one, but a matrix, and then you define the definition of the column space, and the notation is like this. Again, it's not an easy definition to see it, to see for the first time, but if you saw it before, it shouldn't be that difficult. So look what it says. It says it's all those vectors. This is all those vectors, or I should say m tuples. It's specifically to this is something which exists specifically in m tuple spaces. All those m tuples which you can produce as a result of this product A and X, where X come from the n tuple. That's a matrix product here. That's what we normally call a column space. I'm not sure if you registered this before or not, but it's a very important thing to remember, that the column space is a very special version of a span. Very special version of a span. That's why I call this a theorem here. Column space is span. That's the official name of this theorem. You can reference it under this name. The reason for that, that's it. The reason for that is this: if you take a matrix and if you start looking at that matrix from the column perspective, so you just give names to every column of that matrix. See, my matrix has how many columns? N columns, right? It's the second index in the notation. That's why I have N symbols here. And every individual column, how many elements it will have? It will have as many as the rows in my matrix M, right? So that's why every individual vector is an element of Rm. So if you start looking at the matrix as a column structure, then the product like this, when you multiply a matrix by a column vector x1, x2, xn, it's simply a linear combination of the columns. This identity, it rests on your comfortable understanding of matrix multiplication, on the process how the matrix multiplication is done. If you multiply a matrix by a vector from the right, this is effectively the same as if you take the linear combination of the columns of that. It's a very important idea. It's a very simple idea. If you're comfortable with the matrix product, it shouldn't be a surprise to you. But it's a very powerful idea. It sits in many different proofs in linear algebra. So it's very worth remembering this idea. But the moment you do so, then look at this. This Y becomes this linear combination, right? Because this AX product is exactly what's spelled out here on the left-hand side. And that's basically the proof of this column space is span theorem. Column space of any matrix, effectively, it's a span of columns of that matrix. That, by the way, explains the notation and the name, column space. Yeah. So from now on, I won't make any distinction between these two concepts, column space and spans. They are distinct a little bit in one regard. Span, it's more general concept. You can construct spans in any vector space, not specifically this vector space.